Alright, welcome back. We're now going to take the next step in illuminating an LED with an Arduino, which is instead of just blinking it on and off at full brightness for high and zero brightness for low, we're going to simulate sending it an analog voltage, a voltage that's not 5 volts or 0 volts, but it looks like it's somewhere in between. Now the microcontroller can't actually do this, but it uses some circuit magic that's very similar to the way we had a 1 and a 16, say, and when we turned the light on for a brief amount of time and off for a longer amount of time, we got this barely illuminated LED. And as we lower the amount of time that it's off, the LED will look brighter and brighter. Now we're not going to manually do it with digital right on and off statements like this. We're going to use a special command in the Arduino that uses special circuitry in the microcontroller chip to do this at a much faster rate than we could do it manually, and with a much smoother result. But the first thing we need to do is talk about the fact that we're using pin number 2. Let's say we wanted to arbitrarily change to a different pin number. Let's say, in fact, I'm going to unplug the circuit, and I'm going to arbitrarily move from pin number 2 to pin number 3 right next to it. And when I plug my Arduino back in, my program is still running and I'm still blinking pin number 2 on and off. The problem is I'm no longer plugged into pin number 2, so I don't see the correct output. So okay, that's not that big a change. We could just go in here and say, okay, pin 3 and pin 3 and pin 3. I'll go ahead and set these back to 500 so we see the regular blinking. And when I upload that, you will indeed see our good friend, the blinking LED. Now on pin 3. That's great, but what if I didn't have 1, 2, 3 statements that used pin 3? What if I had 2,000 statements? Do I want to go through and change a program in 2,000 different places every time my hardware configuration changes? No. So what I want to do is I want to use the power of the programming environment, and up here at the top I'm going to type a new command. I'm going to type const and then int and then LED in all caps, then an equal sign and a 3. So what I've done is I've declared a variable. In particular, it's a constant variable. So the const, which turned orange, means constant. It's a particular type of variable storage. The int means it's an integer, so it takes up a particular amount of memory in the Arduino chip. The LED is completely arbitrary. That's the name that I have chosen for my variable. The equal sign means I'm going to put an initial value in there, and that value is going to be the number 3. Now because it's a constant, it won't be able to change during the program execution, which is fine because we're going to use this variable to store the number 3 that equates to the pin number I'm hooked up to. And that wiring is not going to be changing during the run of our program. Now, if I come back a month later and I put it on pin 5, yeah, I want to change this to a 5 once, and then recompile the program. But it's not going to change over and over again as the program's running. So a constant that can't be changed when the program is running is exactly what I want. So all I've done is defined a variable, a constant variable in this instance, and a variable is simply a name for a memory location. So it sets aside a bit of memory, in this case a particular size of memory that's enough to store an integer value, a whole number, I think up to a maximum value of something like 32,000. So it's negative 32,000 to positive 32,000. And I have named that memory location LED. And I've put an initial value of 3 in there, which because it's constant can't be changed. All of that means that basically down here where I typed 3 before, instead of typing 3, I can now type LED. And here again where I typed 3, I can type LED. And here, LED. And when I compile this program, all of those LEDs are going to get replaced with this constant value of 3. And the end result is exactly the same. But let's say that I later now move this wire over to pin number 4. Instead of going through the entire program and changing all of those, I can just change this to be a 4, or a 7, or a 10, depending on how my hardware is configured. So it's very common to see a bunch of constant, integer, and then arbitrary names defining all the pins that we're using for a particular program. I need this to be 3 in particular because we're plugged into 3. And now we'll get back to the main point of this demo, which is not blinking the LED, but writing what looks like an analog voltage. The reason I needed to change from pin 2 to pin 3 is look at pin 3 and this little tilde character next to it. Down here it says digital pins and then in parentheses PWM and a tilde character, which means that every pin that has the tilde character is able to do this special function called pulse width modulation. And pulse width modulation is basically the Arduino can be put into a mode using a special command where it turns the voltage on and off to whatever pin has a tilde incredibly fast. And it can change the duty cycle, how long it's on versus how long it's off, to send what looks like the equivalent of 0 volts, or 5 volts, or 3 volts, or 2.5 volts, depending on how we define the right command for that individual pin. So to try it out, I'm going to go down here. I'm going to erase just this portion inside the loop. And I'm going to type my new command up here in setup after pin mode. The new command is going to be analog write. And it needs to know 2 things. First, what pin do you want to analog write to? That pin is called LED. And what value do I want to write to it? I want to write a 0. Let's upload that. And indeed, I see the equivalent of a digital write low, an LED that is not on. Instead of 0, let's try another number, 255. When I upload that, I get a bright LED. That's the equivalent of a digital write high. Now, why only 255? Why not 256? Because we started at 0. There are 256 values from 0 to 255. And that's the range of values that the analog write command requires. 256 values from 0 to 255. If I do 256, what do I get? Very simply, I get the equivalent of a 0 again, because after we get to 255, if we take one more step with only 256 values, we're at the equivalent of 0. So we've looped back around to 0 by using 256. All right, so instead of 255, let's try roughly half of that, which is 127. And we get this. Notice that it's a less brightly illuminated LED. I'll go back to 255 so you can see the difference. So keep an eye on the LED. There's a fully bright LED. Here's the 127. So the first LED was getting something like 5 volts. That's getting something like 2.5 volts. It's not actually getting 2.5 volts. It's getting 5 volts half the time, which in pulse width modulation terms is a 50% duty cycle. Half the time it's on, half the time it's off. So it looks like an equivalent of half as much voltage. And indeed, the LED responds in the way we would wish it to by being about half as bright. Let's go down to, say, 63, which is about a quarter of the value. Starts to get dimmer. Then we'd have 31. These are all 1 less than half of the base 2 value. And at that point, we're pretty weak. I can see it in the room, but it's barely visible on the camera. So 16 minus 1 would be 15. Still illuminated, but getting hard to see. We can do a 7. And of course, we can do arbitrary any values between 0 to 255. So instead of just writing a single value, let's do something interesting in the loop. So I'm going to remove this analog write, and I'm going to put it down here in the loop. But instead of doing it one time, I'm going to use a new concept called a control structure. And a control structure in a programming language is a programming structure that lets you change the number of times functions are executed. So far, all of our functions have been executed top to bottom one time. Pin mode got ran once, analog write gets run once, and of course, because we're in a loop, which in itself is a hidden control structure, we go back around to the top and we do it again. But we as programmers are not choosing to do any different number of executions of analog write, aside from the fact that we've put it inside the loop so it happens over and over again forever. But now we're going to have it happen a specific number of times. We're going to use something called a for statement. So we're going to type the word for, and then in parentheses, we're going to type integer I is assigned 0 with a semicolon. I is less than or equal to 255, semicolon, I plus plus, and a closing parenthesis. So all of that, another curly brace, and we'll increment the position of the write statement, and then a closing curly brace. And notice that it matches up our curly braces for us. So we can see that here's a for statement, here's a bunch of stuff that defines the for statement, and everything between these two parentheses is what happens every time we go through the for statement. So what we've done in defining the for statement is we've created a new local variable called I. It starts out with a value of 0. We're checking to see that it is always less than or equal to 255. And every time it is, we're going to increment its value by 1. So I plus plus is shorthand for I is assigned I plus 1. And then we execute what's inside the loop. Well, right now it's an analog write of LED 7, which would basically just sit there and give us this brightness forever. So instead of the 7, let's do I. And when we upload that, what we're going to see is the brightness starting at 0 and going up to full brightness and then repeating. But we've broken the first rule again, which is what? Computers are very, very fast. So that's happening so fast that we don't see the result. We have to do a slight delay. And let's do a delay because we're doing a bunch of writes over and over again. Let's start with a delay of 10 and see if that's enough to see the effect. So we have a 10 millisecond delay, and indeed, we start at 0 and we go up to full brightness. And then as soon as we get through the loop once, we fall out through the bottom, and the larger loop function brings us back around to the top where we reinitialize I to 0. We write a 0 value to the LED. We wait a little bit for the humans to see the effect. Then we check to say, are we still less than 255? Yep. Okay, so now do a 1, then a 2, then a 3, then a 4, and that continues until I is no longer less than or equal to 255. So as soon as we get to 256, we're done with the for loop, we fall out of the bottom, and we go back around to the top of the whole master loop. So we start at 0, and we go up to full brightness, and then we cut back to 0 and go to full brightness, back to 0, full brightness. That's nice, but we can make it even cooler. Let's take all of this and copy it this time, and let's put a second copy of it right here. So we went all the way from 0 to 255 from darkness to full brightness. This time, let's do the opposite. Let's start at 255. Let's make sure that I is greater or equal than 0. And let's do I minus minus. So this is just the opposite for loop that starts at a 255 value and counts down to a 0 value. And that's going to happen right after we go from 0 all the way up to full brightness. Then we're going to go from full brightness back down to 0. But now instead of cutting, we're going to do it in a smooth manner. Let's compile that and see the difference. So we go up to full brightness, and then we fade back down. So we get this nice smooth fading up and down effect. And you get this sort of Apple computer blinking power light that fades up and down slowly. And we could play with these values. We could do a different delay in there, which would just make things happen slower. So if I double the delay on both of these, we get an even slower fade up and down. So this technique, this analog write, is useful for blinking or fading LEDs up and down. It's also very useful later on when you are controlling electric motors, especially using something called an H-bridge, which I'll give you some references for in the supplemental materials. So this would be the exact same way we would change, for instance, the motor speed of a robot's left and right wheels to go from 0 velocity to full velocity. So this would be ramping from 0 up to full speed and then ramping back down to 0 again for one wheel, for instance. And instead of writing the pin that's connected to an LED, we would then write a pin that's connected, say, motor left or motor right. And there'd be some additional circuitry that would allow the Arduino, with its very low voltages, to control a much larger voltage in a motor. We'll learn more about that as we go along. But for now, we have a beautiful fading LED. So let's finish this lesson by just enjoying that.